Welcome back to another episode. Today we're going to be learning about orbit energy. As we see on the board, we all know that total energy is the kinetic energy plus the potential energy, and that the energy is conserved. Then how can we write the energy equation for an orbiting satellite? I don't want to disappoint you guys, but it's literally very similar to the top equation, and probably the equation that you guys are very familiar with. On the bottom, we have E equals 1 over 2 mv squared minus capital G, capital M subscript E, and times m over r. So let's talk about all these variables. Okay, so we have a capital E that has to be the total energy that includes mass, right? We have mass in our equation, and m is a mass, v is the velocity, and there are some values that we might be not comfortable with. So g is actually the universal gravitational constant. And so far in the physics world, this gravitational constant is uniform all across the universe. And obviously, the capital M with subscript E is the mass of Earth. And the small m is the mass of the satellite or the spacecraft. And r is the distance between capital M, from the distance from the center of the Earth to the center of the spacecraft. So I'm just going to write distance here. So from this equation, which is our satellite energy equation, we can divide this entire term by mass. And that would give us the specific total energy, which is a small e, and then we won't have the small m, which is the mass. And I guess I have to specify that we're dividing it by the mass of the spacecraft, which is small m, the lowercase m. And so we have this. The reason why we can divide by m is because it still has the same significance of the meaning for the equation to work. The mass of this spacecraft doesn't really have an impact in the meaning of this equation. And what we also do in the astrodynamic world is we combine this term, capital G times the mass of the Earth, and we say that this is a mu. And I want you guys to be comfortable with this value, mu. It's just a constant. It's like pi, but it's just easier to use mu in the astrodynamics because we have a lot of the same, like capital G times the mass of the Earth, and we don't want to write two terms. We just want to write one symbol, and it's just so much easier. So let's just clear it up and write the whole equation once again. So here we have it. Small e equals 1 over 2 v squared minus mu over r. Okay, so we talked about the potential energy and how potential energy is a negative value. So I think we can move on and we can use this elliptical orbit and talk about how velocity and potential energy changes and converts with each other. So let's talk about, I guess, point A. R is really big, right? R is far away. The satellite is far away. What does that mean? Again, potential energy is approaching 0. And again, it's approaching 0 from the negative side, right? Okay, what does that mean? Well, that means velocity is actually lower because we have to maintain a constant energy. We have to maintain the constant energy for the orbit. Let's talk about point B. Our r is getting smaller because we're getting closer to Earth. That means potential energy is having a larger negative value. Larger negative value. What does that mean? It's becoming like, negative 25 and then negative 100, maybe a negative 1,000. It's a large negative value. Well, what does that mean? If the potential energy is becoming very, very small, as in a large negative value, in order to keep the total energy conserved, velocity has to be greater because we have to compensate with that very large negative value. And the energy for A and B has to be the same. So there you have it. We learned the orbit energy equation. E equals v squared over 2 minus mu over r. It's simply the normal equation, kinetic energy plus potential energy. The only weird thing is that in this astrodynamics equation, we have potential energy to be negative, and as r gets really, really big, our potential energy approaches 0. So that's it, guys. Thank you for watching this video, and I'll see you guys in the next episode.